the entire chapter. It should have 12 pages, so please double check that you have all 12 papers. And will you please write your name on it? Please, please, please. That way, if you forget it, I can give it back to you because this is a lot of expense to print all this paper out. I get that it is necessary for geometry because we have so many figures. Okay, so please put your name on there. Alrighty. Today we are classifying triangles by their angles and sides, which you have probably been doing since 4th, 3rd, 4th, 5th grade, somewhere around there. You learned a lot of these things back then. We're reiterating them again today. But the part that you are learning today is that we're actually going to be proving some of these classifications using coordinate geometry. And so we're going to do some coordinate proofs, is what they're called. And Delta Math does a really good job of walking you through everything you need. So today we're going to learn how to prove that we have a right triangle, and we can easily prove things by how long the sides are. So we'll be figuring out if we have a right triangle or not a right triangle, and we're going to figure out if our sides are either scalene, isosceles, or equilateral. But before we get to coordinate proofs, we need to just relearn some terms here. Scalene means what? No congruent sides. It says it right there. It means that each side is going to be a different length. So we have a short side, a middle side, and maybe a longer side. 3 different side lengths is a scalene triangle. What does isosceles mean? Yeah, at least 2 sides congruent. So you can see I'm marking them. We do want to make sure this unit that we are learning how to mark our figures up correctly because it's going to really help when we get to proving congruent triangles. All right, so isosceles says at least 2 congruent sides. And then equilateral is all 3 sides are congruent. All right, 3 congruent sides. So, question, does that mean an equilateral triangle is also isosceles? It does. Because does it have 2 congruent sides? It sure does. And it has another 2 congruent sides and another pair of 2 congruent sides. It is a subset of isosceles. A very specific one. All right, so we can classify triangles by angles as well. We have an acute triangle, which has 3 very acute angles. What are acute angles? Smaller than 90. Look at you multitasking over there. Smaller than 90 degrees. It's a cute one. All right, what's a right triangle? Exactly. It has 1 90-degree angle. Exactly 90-degree angle. 1 90-degree angle is all it can have. And then an obtuse triangle. What's an obtuse triangle? 1 angle happens to be very big. 1 angle happens to be greater than 90 degrees. Greater than 90 degrees. And then equiangular triangle has 3 congruent angles. Yeah, so you see the markings there. All 3 angles, and yes, they would all be 60 degrees. You're right, I heard that. Which we'll talk more about tomorrow or the day after, I think. Okay, so we have example 1 here. Determine the types of triangles shown. And in Delta Math, they give us some lovely little triangles to look at. And these are all the options. You can see they get pretty specific as to which one we have. So we need to look at the sides and the angles. So to start here, let's look at the sides of this first triangle. Tell me about the sides of this triangle. None of them are congruent. They're all different. All right, we've got 7.13, 3.11, 4.88. All those are different, which means scalene. All right, and then if we look at the angles, tell me about the angles. Yeah, we have one angle that's obtuse. And so that means that it is an obtuse scalene triangle. One obtuse angle makes it an obtuse triangle. All right, let's look at letter B. Tell me about the sides. Tell me about the sides of this triangle. Two of them are congruent. And I'm going to mark that on my picture. Make my little tick marks there, congruent marks. Two sides are congruent. What does that mean if we have two congruent sides? Isosceles. All right, two congruent sides is isosceles. Now tell me about the angles. Pardon me. One of them is 90 degrees. Tell me about the others. They equal each other. We got two congruent angles in there, but I don't really care about those. We have one 90-degree angle, which makes it a right triangle. So this would classify as an isosceles right triangle. And then my last triangle here, tell me about this one. Tell me about the sides. Two congruent, we got 4.92 and 4.92. Two congruent sides means isosceles. All right, two congruent sides. Tell me about the angles. Yeah, I do have two congruent angles, but I don't have a special name for two congruent angles. What else do we know? They're all acute, which means all less than 90 degrees. So that makes it acuity, Okay. Yes, isosceles acute for that last time. Okay. Alrighty, last example here. Again, Delta Math does a great job of walking you through these proofs. And this is where colors is going to be real helpful. So if you've got a few colors, I'm using 4. Boys, this is called teal and pink and purple. And like a black pencil color. Graphite or black, that's the only colors you can. Hey, that's my color. Okay. All right, here we go. We are going to graph the triangle and classify it by finding the lengths of sides and or slopes. So today we can do a lot with the lengths. The lengths are going to tell us if we have a scalene, isosceles, or equilateral triangle. All right. The slopes are going to tell us if we have perpendicular lines, which would mean we would have at least one right angle. All right. So all we can prove today is that we have a right triangle or not, and whether or not it's scalene, isosceles, or equilateral. So we're going to start by graphing our ordered pairs. So 1, -3, and I'm going to label it a W. I have -4, -7, which is right here, and I'm going to label that an X. And I have -8, -2, right there. I'm going to label that a Y. And I'm going to connect those with as straight lines as I can draw. There we go. So I have a nice little triangle. Now I'm going to take my color. And I have a couple things I need to do. So I need to find the slope of WX, which is this lovely little segment here. We can find slope by talking about rise over run. And what I'm going to do then, and I'm going to do this because I'm going to use it more than once, so this is a really good thing to do. I'm going to look for the little horizontal and vertical component that gets me from X to W. So I have my horizontal piece and my vertical piece. What's the length of my horizontal? A little bit here. 5. Very good. And the length of my vertical piece? 4. And is this line XW, is that a positive slope line or a negative slope line? Positive. It's going uphill. So I'm going to just assign a positive. The rise is 4. That's the vertical bit. It's 4. And the run is the horizontal piece, and that's 5. So we get positive 4/5 for our slope. All right. I want to find the slope of XY. Going from X to Y, I have a little horizontal component and a vertical component. What's the length of my horizontal component? 4. And again, we're going to use these marks again, so having them on paper is really nice. And the vertical bit? 5. Good. Now, when I look at this line, XY, is that a horizontal, a positive slope line or a negative slope line? Positive. It's negative. It's going downhill from left to right. So it is going to get a negative. So I'm just going to put on the negative, and then I don't have to think about it. And the rise is 5, and the run is 4. Ooh, what do we know about those? Yeah, they are perpendicular. How do we know they're perpendicular? Because opposite reciprocals. Very good. Perpendicular because we have opposite reciprocals. Excellent. All right, we want to find the slope of YW as well. So again, I'm going to do my little horizontal bit and my vertical bit there. What's my vertical component? 1 space. And my horizontal? 9. All right. So is this line a positive slope or negative slope? Negative, yeah. So we get a negative, and the rise is 1, and the run is 9. So we get a slope of negative 1/9. Negative 1/9. So what do we know? We can find the lengths by doing the Pythagorean theorem. You're absolutely right. But before we do that, what do we know for therefore? So we do have opposite reciprocals. So we know that WX is perpendicular to XY. WX is perpendicular to XY. What do perpendicular lines create? Okay. All right. So WX is perpendicular to XY, and that's going to give us a right angle. All right. So that's our right angle right there. Now, as was said, we also need to find the side lengths, and that's what this means here. The WX, it doesn't have a segment above it, and when that's missing, it means find the length of segment WX. So we want to find the length of this line, and as Wyatt said, we can use the Pythagorean theorem to find a slanty length. All we have to do is do the square root of leg squared plus leg squared. So anytime we have a slanty length, we just need to take the square root of each leg. And we've already drawn in the legs, which is why we took the time to draw them. So to find this lovely slanty length, it's just going to be the square root of leg squared plus leg squared. So square root of 5 squared plus 4 squared. All right. What is 5 squared? 25. And what is 4 squared? 16. Now, I'm going to caution you here. We, as math people, 5 squared plus 4 squared under the radical is a giant ugly answer. All right. Does this decimal stop? No, it does not. It goes on forever. Our calculator stops giving answers. That's what it does. But it goes on forever. It's irrational. It goes on forever. Can I math frac it? No, you can't math frac something irrational. It's totally crazy. It'll never work into something nice and rational. Okay, it's irrational. Now, because of that, Delta Math would rather you just say, hey, let's just do 5 squared plus 4 squared. And that's 41. Let's just do square root of 41. Look at that lovely exact answer. Isn't it nice and neat and succinct? It doesn't go on forever. Radical 41 is a way better answer than something that gets rounded off, okay? So you get to leave it as a radical 41. All right, xy is right here. It's a lovely little slanty line. How are we going to find the length of that slanty side? Same thing, square root of 4 squared plus 5 squared. Should give you the exact same thing. Hey, what do we see there? Two, at least isosceles, 2 congruent sides. I guess we might have one more, so let's check our last side. We could have an equilateral triangle. All right, last side here. How do we find the side YW? Square root of 9 squared plus 1 squared, which is 81 plus 1, which is 82. So that's not the same. All right, so we have 2 congruent sides. I'm going to mark that. There's one congruent side and the other congruent side. So we have an isosceles. Isosceles right triangle. 2 congruent sides and a right angle. So it's all fill in the blank and that's math, so, and then it's been dropped down. Super nice. It's super nice. All right. Now, when I was in school, we had to do these, but we didn't get graph paper and we didn't graph them. So we just had to calculate slopes like we did in the Bauer and use the distance formula to find these. This is way easier, you guys. It's totally easy. Okay. Let's do one more. All right. V is -9, -1. W is -1, 5. And X is -6, 5. And I can connect those with some straight lines and you'll have a little triangle there. Hey, yeah, you sure do. All right. Okay, the slope of BW, again, I'm just going to draw in my little legs here of a right triangle to make life easier for me. Horizontal, vertical component. So what's the slope? Let's see. How long is my horizontal bit? 8. And what's the vertical? 6. And so the slope is 6/8, which reduces to 3/4. It probably does want you to reduce fractions, I would assume. All right, WX. Oh, WX. That's a nice flat line there. Do I need to calculate the slope of that? What is the slope of that? Curtis. What's the slope of that? That's the length. Right answer to the wrong question. Yeah. The slope of 0. It's not a positive slope. It's not a negative slope. In between positives and negatives is 0. Okay. Slope of 0. And the slope of XB. We have a vertical component and we have a horizontal component. Let's see, which is up 6 and over 3. What's the slope?
I think 2.
Positive. The rise is 6 and the run is 3, which does in fact reduce to a slope of 2. Good. What do we have any perpendicular lines here?
Yeah.
No, that'd be a hard no there.
No.
No right angles. Because we don't have any perpendicular lines, we don't have any right angles. And that's all we're figuring out. Do we have a right triangle or not? So we don't have any right angles. No perpendicular lines, no right angles. Yep. Okay, let's look at the length of VW. How do we find this slanty length? Square root of 8 squared plus 6 squared. Good. And let's see, 8 squared, thank you. 8 squared plus 6 squared gives me 100. So that's, what's the square root of 100, ladies and gents? 10. Helen, right. Okay, thank you. Thank you. All right. Okay, and then WX. All right, here's your question, Curtis. WX is how long? 5. Do we need to do the slanty, or sorry, the radical thing?
No, because you can just count.
You can just count. Yeah, it's a nice horizontal line. You can just count it. If it was vertical, you can just count it very easily. Okay, now we have another slanty line here for VX. How do we find the length of VX? Square root of 6 squared plus 3 squared would be a little better. All right, so 45, 36 plus 9 is definitely radical 45. Are any of these the same?
No.
None of them are the same. No congruent side. Okay.
Whoa.
Oh.
All right, we have no right angles. We have no congruent sides. What kind of triangle has no congruent side?
Similar.
Scalene. And not right. Triangle. We haven't proven obtuse. We have proven that it is not a right triangle. We have to do some more math to prove that that's an obtuse angle. We can assume it. We can look at a picture and say, hey, it looks obtuse, but we haven't proven it, which is a different thing.
But like,
Maybe.
because it
It's
doesn't.
not 90. It looks bigger than 90.
It
It
has
definitely is, but we haven't actually proven it. We're looking at it. I know. We're not doing that today. All right, ladies and gentlemen, you can get started on the down
I just put it out.
Okay.